So again, what we want to do is this. Yeah, so we need to create the Verilog code to describe this. Okay, but first we need to look at our DU, because I think DU last week we don't have this yet, so we need to add this. Oh, we have already. We have output R1, R2, R3, R4. So this is okay. Yeah. So now we can create this DUCU. We can call it Ucu Integration. Now we need to add the file because we will use the DU and CU here. First is of course the DU must be here, and the other one is the CU. Okay. Okay, so need to have this module, and the clock, the reset must be there, and also I think we need to list all the input output that we have. So maybe we can just copy from here because this is same thing. Okay, so here are all the input output that we need to have. Okay, we need to have clock, reset, and we need to have the start signal as well. The start and the state. Right, remember the start and state in the CU, and X done and Y done must be there also. Input same as this one. All the input here we need. But not LD1, LD2. So again, because LD1, LD2 and until SEL is actually not the input or output. Yeah. So this is a wire. So here I need to remove. Here we have only this for the input and output. Clock, reset. Look at this. We have, of course, we need to have the clock and reset. Right? So we need to have clock, reset. Clock, reset. R1, R2, R3, R4. R1, R2, R3, R4. Okay, there, A, B, C, D, E, here, A, B, C, D, E, and we have start, we have state and X done, Y done. So X done, Y done is here. Actually, we have another one, state, right, to see the state of the CU. So that's it for the port. Input, we have clock, we have reset, we have start, and that's it for the 1-bit input. We have also 8-bit input, R1 to R4 are the 8-bit, and then we have the output. This is not input, sorry, this is the input here, A, B, C, D, E, right? Not R1, R2, R4. A, B, C, D, E will be the input. Any other input? No, right? So we have this input, start, clock, reset, then done. Other must be the output. So 1-bit output is the X done and Y done. We have state. What is the size of the state? 3-bit, right? We have state. We have 8-bit output, which are the R1 to R4, right? That is, and we have the wire, right? This will be the wire, LD1, LD2 until SE, LA, all are the wire. So we have that. I just copy this, make it wire. All are 1-bit wire. And I have 2-bit wire, which are these two are 2-bit wire. Anything else? I think that's it. Now we want to instantiate DU and CU. So we want this to be here, all right? And we call this as data path, right? And the port connection, we will use the port positioning syntax, right? This is easy, such that we can just copy this and put it here, right? I can use this because I use the same name as this one, right? That will be the DU. And I also need to have the CU. So where is the CU? This is the CU. So the name is this. And I name it controller. And inside must be this. Should be the same, right? Because the name is, again, is the same as our port declaration here. So This is no problem then, right? Now we connect all the things already. Okay, so we have the CU-DU integration already, means that this circuit is done. And observe that we use hierarchical design methodology, yeah, where this is the subunit and this is the subunit, right? And the connection is described here. Okay, so we save and try to synthesize the design and see whether we can get the design, the correct design or not. This looks like everything is okay. Here we don't have any error, right? And when you expand this, you can see here in our design we have two sub design or sub module. The first one is the controller, the second one is the data path, and here is the controller and this is the data path. And if you look at the netlist viewer here, Rtl Viewer, so you can have, or you can look at the design where this is the controller and this is the data path, and all right, all the connection is like this. When you double click here, this is the data path that we have. Okay, and when you look at the controller, here is the controller, right, created by the software. Okay, so we have that already. Now we can create the test bench. So let's do detachment. We have the time scale 1 nano to 1 nano. Okay, let's use this name as the attachment name. And yeah, of course, we want to use this. So we can just copy this and have here, change this to rect. This should be rect. Wire. Wire and wire. Right. Now we need to instantiate our design here as the design and the test. So our design is this, means that we have this one. Okay, and we name this as a DUT, design and the test. And the port, again, we use the port positioning syntax such that we can just copy and paste there. Right, now we have everything here. We can create the clock signal. So we can have the clock. Our clock name is clock. So we can have clock start with 0. Maybe every 10 nanosecond we change or toggle the clock, right? So this will create the clock with 20 nanosecond period, right? Because we toggle the clock every 10 nanosecond. Okay, now we give the input stimulus. So we can we can start with when at time 0. Time 0, so we reset our design first. Yeah, reset, and let's say our A is 1, our B is 2, C equal to 3, D equal to 4, and E equal to 5, and we not start yet, so start equal to 0. And for example, another 30 nano, we set, or we make reset to be 0, not active, and we wait another 20 nano to have the start signal equal to 1. Another 20 nano, start signal go down to 0 again, and we wait, for example, for 100 nanosecond. Another 100 nanosecond. Now we change, for example, we changed A, B, C, D to a new value. Maybe A equal to 2 now, B equal to 4, C equal to 6, D equal to 8, and E equal to 6. And we set the start to be equal to 1 and make it equal to 0 after another 20 nano, and we wait for maybe 100 nano to stop the simulation. Right. Okay, so that will be our stimulus. So we have two set of input, yeah, where the input value will change after certain amount of time, 50, 170 nanosecond, and we change the value, and we should expect the correct result in R1 and R2. Okay, so let's save this. And to be safe, let's check for any syntax error. And again, we need to wait. So we have no errors, means that this should be okay. Now we try to do a simulation where we need to have some settings here. We need to use the compile the test bench. Test bench, the name of the test bench, and need to add the file here. This one, add. Okay, and yeah, run the RTL simulation. Okay, so we have the output here, but all of this are in binary. So let's change this to unsigned decimal, and let's look at this, the result. Yeah, the simulation result. So this is the state. Put it down here, state. Here are the input, yeah, R A, B, C, D, E. So we have 1, 2, 3, 4, 5. And here we change the input from this value to 2, 4, 6, 8, 6. And we can see that the output here, yeah, R1, in R1 is, we need to look at this. In R1 is X and R2 is Y. So X is 30 and Y is 28, right? So if you substitute the value here, for example, X is 1, B is 2, C is 3, right? So 3 plus 1 plus 2, you have 6 here. E is 5, right? So 5 multiplied by 6 is 30. So we have 30. And this is 28. So A is 1, C is 3, 4. Multiplied by 3 plus 4, 7. 7 multiplied by 4, you have 28. 28 in R2 or Y, right? So when you change, you can see that the value of X and Y is this. So if you put the number in the equation here, you can get this. Yeah. So the things that we need to observe is here. Yeah, look at this, the state. All right. So when we reset, yeah, we will be always in state 0 until wait for the start signal to be asserted here, to be activated here, to be activated. And when it is activated, it will change to, yeah, because our controller is negative H clocked, negative H triggered. We can see that when clock is negative here, it will change to state number 1 whenever the start signal is activated, right? And at state 1, what we do is we load, right? Remember what we do in state 1? We load A into R1, B into R2, C into R3, D into R4. Now we can see here R1, R2, R3, R4. We can see that now the value is loaded. Yeah, from before this 0, nothing there. When we load in state 1, 1, 2, 3, 4 is in R1, R2, R3, R4 already here. And why I said before that for the CU we use negative H triggered, but in DU we use positive H. All right, why? That is because we want this. We want the state change first before the data is loaded. You can see that we change the state at the negative H, but we load the data at the positive H. You can see that the data is loaded at the center of the clock here, all right, of the state here, right? Because this is important. If you load the data, yeah, in practice, if you load the data at the beginning of this, yeah, you might sometimes miss the value, because in order for the register to be stable, yeah, there is what we call the settling time, right? So before the data can be loaded into the register, so we want to make sure that everything is okay first. Here we can see that we delay half clock cycle here before we can load the data. And because we set, yeah, in our design that we load the data at the positive H, of the clock. So the first negative edge, we change the state, right? The state is stable now. We load the data. So here we should be safe, right, from any signal delay or whatever, right? So that's the reason why we have different clock edge flip-flops. And the next, this is state number 2. You can after this you can check why state number 2 we have 3, 4, 7 here, and so on and so forth. And you can see that in state number 3 we get the result for y already, because look at this. Yeah, y. And remember, we changed this already. We have another state before this. We call it S0. This is S1, S2, S3 in our design. So S3, we have Y already. That's why we have Y here. And we have Y done equal to 0, equal to 1. Means that this indicate that Y, yeah, the result for Y is ready. And here, state number 4, we have X ready, and X done is activated to indicate that this operation for X is done. All right, and we wait for the next start signal to be activated. And if data change here, we change the value, input value here. This new cycle will be started here when we activate the start signal, and the process repeated 1, 2, 3, 4, and we get the result. All right, so that is how the things work. The one that we do is actually this one, number 1. So number 2, what you need to do is to apply the course level restructuring on the equation of X. Means that this equation to allow for minimal hardware implementation, and derive the DFG and design your corresponding data paths, applying the constraint resource allocation of 1 multiplier and 1 adder. Also apply ALAP as late as possible register allocation. So for this question, what you need to do is you need to alter the equation a little bit, such that you can have something like this. Because if you look at this, yeah, you have x is e multiply a plus b plus c, and you have y is okay. Yeah, let's write y first, c plus d. So when we look carefully to the equation here, we can spot something. We have this a plus c, and we have a plus c here, right? So what we can do is we can actually have this multiplied by this, such that we can have a plus c and a plus c. And if we have this, actually we can share the hardware. Means that the hardware is the same as compared to this one. This is different hardware, right? So if you do this, your DFG will look something like this, where you can start with A, C plus B multiply E, you will have, of course, X here, right? And here is the good thing, because this is A plus C, you can use this already, such that this is A plus C. You have one more, which is C plus D, right? Multiply, and you have Y here. And see this. If we compare this with this, all right, so we can reduce the number of operation already. So we have here one, how many at 1, 2, 3, 1, 2, 3, 4, 5. Here we have 1, 2, 3 only. See, 1, 2, 3 add. Now we reduce the number of hardware already, right? So that is the meaning of that. And for the scheduling, now you are required to have or to use only one multiplier and one adder, meaning that in this case we have 3 adders. Now we are constrained, you are constrained to have only one adder and one multiplier. One multiplier is okay, because here we use one multiplier, but how to use one adder now, right? So that is interesting. Yeah. This is not that difficult, because we can see here, if we schedule this like this, right? So see this, we have 2 adders here. So to make it 1, what you can do is that you can actually move this operation before. This is C, right? So C, A, okay, A plus C, and this is C plus D here. Multiply, and you get Y. B, you have this. Multiply, you have X. Now you can see that you use only one adder, and of course here will be S0, S1, S2, S3, S4. You can see that the number of cycle is added one more as compared to the previous one, where you have only S0, S1, S2, S3, 4 cycles. But when you have the constraint, now you need to have 5 cycles, but you only 5. You see here, the good thing is that you only add one cycle, yeah, the speed is lower. Yes, a little bit lower as compared to the previous one, because this one you need 5 cycle, but only 1 cycle lower. But in terms of cost, which is very important in design, right? You now can reduce from 3 adders to 1 adder, right? So you reduce the cost a lot, right? So this is how we do the optimization. We optimize at the one is at the equation algorithm level, and the second one is at the uh, schedule level, at the hardware level, right? So that is how we do. So try to do this. Yeah, the answer is, yeah, I give you the answer already actually, but try to have the RTL code, try to do the scheduling and allocation, and derive the RTL code, and of course derive the data path and control unit, and then the simulation result. Yeah.